This video is sponsored by PCBWay. Hey there, this is Seth Schaefer from Team Just Cause Robotics, and in today's video, I want to talk about autonomy in Battlebots. And really, are combat robots even robots at all? This video will be a discussion talking about robots and automation both inside and outside of a battle box. We'll talk about some examples of machines that are undoubtedly robots, and then why I feel that Battlebots and combat robots in general do in fact count as robots themselves. After that, we'll talk about what sorts of autonomous features can actually be implemented and the complexity involved in creating those, and what are generally the advantages and disadvantages of adding autonomous systems to combat robots, plus why we don't see more of them. What exactly is a robot? Well, according to Wikipedia here, a robot is a machine, especially one programmable by a computer, capable of carrying out a complex series of actions automatically. A robot can be guided by an external control device, or the control may be embedded within. Robots may be constructed to evoke human form, but most robots are task-performing machines designed with an emphasis on stark functionality rather than expressive aesthetics. Personally, I think this definition fits Battlebots quite nicely. These robots are designed with one purpose in mind, and that is to destroy the other robot, just like how any military-style robot would be designed to fight. And they are controlled by an external controller, though they have some autonomous functions in some cases. Oftentimes, the only autonomy is limited to what a speed controller is doing, but I still feel that that meets the definition of a robot, and I'll get into that further in the near future. I think that really the thing that most people get hung up on when they say that combat robots aren't robots is that they aren't doing enough automatically, or in other words, they don't really display a high level of autonomy. Think self-driving cars, right? A self-driving car that has, let's say, level 1 autonomy, it might be able to, cruise control, but you still have to drive most of the time with something that has just, adaptive cruise control or whatever. You're still doing a lot of inputs. Similarly with a combat robot, most of the control is input with one of these, which is a standard, RC radio transmitter. But that doesn't mean that they don't have any autonomy whatsoever. To start off, let's talk about examples of where autonomy has been used before. The most notable example of this is, of course, Chomp in Battlebots. So right here, I'm going to play a clip from a unaired Battlebots fight between Chomp and Kraken. This was back in 2019, or Battlebots 2018 rather. This is posted in 2019. It's one of the basement tapes where there's raw fight audio only, but I'm leaving the audio out for right now. Now you'll notice there's a weird symbol on top of Chomp. I worked in the Robotics and Artificial Intelligence lab at the University of Rochester, where I went to school for mechanical engineering for one summer, and I also took a couple autonomous robot controls classes with the professor who was, in fact, the director of the Artificial Intelligence lab. Those symbols, like the ones that you see on top of Chomp, are what are called April tags. They are used extremely frequently in the robotics industry. Basically, an April tag is just a black and white symbol with a bunch of really large squares that are either filled in or not filled in, kind of like a QR code. But the nice thing about an April tag is there's only a few different April tag symbols, and because they are well-known symbols, they can be autonomously recognized by computer vision systems, and as long as you have information as to how big the April tag is supposed to be when it's printed out, that means that a vision system can actually see the April tag and know exactly how far away it is, even with just a two-dimensional camera, by seeing what the scale is in the camera image. And on top of that, it'll also be able to determine what the orientation of that April tag is. So in this case, it's basically being used for Chomp to know when it's on its side or upside down, and it's supposed to autonomously be able to self-right itself, as you can sort of see it attempting to do here. Did this work very well? No, not really. But it had the potential to actually save the driver the effort of having to hit the self-right button or whatever. Now, you can also see there was a much bigger Chomp that was made for the 2020 season. So the 2020 version of Chomp is obviously completely different, and it was an absolute monster. I don't think anybody would look at Chomp and say, that's not a robot. I mean, look at that goddamn thing. It's a huge fucking spider creature out of your nightmares. It has 6 pneumatically powered legs. Each leg is actually just being radio controlled by a driver, but Chomp is actually basically 2 robots in one. The turret has its own battery, power system, radio system, everything. It has flamethrowers, has a hammer, and it has pneumatic air tanks in it. And basically the turret is its own separate robot that has the ability to pivot around and to fire the hammer and to shoot flames. And it also basically is supposed to have a radar system embedded in it that was supposed to basically be able to determine where the opponent was and how far away they were, determine exactly when to fire their hammer based on how far away they were, and automatically rotate the turret to face their opponent autonomously. Now, unfortunately, Zoe Stevenson mentioned in a video that was posted to YouTube or Facebook where she was developing Chomp that when they actually integrated the LiDAR system with the turret, it was working fine at first, but as soon as they put that green, like, fiberglass armor on top of it, it unfortunately stopped working correctly. They were dealing with radar reflections around the inside of the armor panel, which is actually a problem that we have personally dealt with at Deco with the radar systems we have in our robots, so I can understand where they're coming from with that. So unfortunately, for all of Chomp's actual televised fights, Jasha was driving the turret side of the robot himself, while Zoe drove the crawling leg side of the robot herself. And so it was actually just manually being controlled, but it had the potential to be basically half autonomous, where the entire top half of the robot was controlled purely via autonomy, and then it was only the bottom half that was going to be manually driven around by Zoe to tell it what direction to turn in and how fast to walk in that direction, etc. I also would like to point out that the legs themselves, each individual leg is being controlled in a very complex manner. When you're driving a wheel with a motor, all you have to do is make motor go spin spin and the wheel turns and the robot moves. Legs aren't like that. Each of these legs had like 3 or 4 independent actuators that had position sensing, and how far a pneumatic actuator was extended or retracted was determined by some Enfield sensors, which I believe sponsored Chomp. To give you a better sense of what I'm talking about with these positioning sensors, this is Enfield's own website, which I got through the link on the Chomp BattleBot page, where it shows that this is one of their sponsors. This is one of their high flow cylinder positioning system valves, and you can see it costs basically $1,000. Now there are 6 legs on Chomp, and each leg had, I believe, 3 of these. So that means that just with positioning sensors alone, there are $18,000 of sensors in Chomp. Not counting the LiDAR or anything to do with the hammer or the turret, that's just for the legs. So this is pretty much reason number 1 that no one really does this, is it's way more expensive than not having these sensors. And there's always a likelihood that the sensors will fail and then your system will kind of break as a result. Now, I'm sure that the Chomp team talked with Enfield about what they were going to be doing with these and got the idea from them that this would be the one that's suitable for their application. Also, I don't know if this is the exact model that Chomp used. The cheapest one is still like $800, so, you know, it's still like $15,000, $18,000 in sensors no matter what. The closest thing that I could say to like an autonomous combat robot that we've seen do well is something like Project Liftoff. Let me show you an example of this robot. So Project Liftoff is a 3-pound combat robot that fights in the Norwalk Havoc circuit primarily. And here's an example of it fighting. It's this white disc thing here. So the way Project Liftoff works is basically the entire body spins as a metal ring with teeth sticking out in the middle of it, and 2 motors that are kind of like hub motors to drive the wheels. And so by spinning the entire robot, you get an immense amount of kinetic energy compared to just spinning the outside of the robot like a shell or a ring spinner would. But because the entire robot is turning the whole time, in order to make it move in any given direction, you need to basically use some computation and programming and sensors to determine exactly how fast it's turning and at what position in the rotation to make one wheel go slightly faster than the other to kind of work its way around. So it will never be able to move in any given direction nearly as fast as a robot with both wheels facing that direction. But it has the advantage of, because it's spinning so fast, it could hypothetically move in any given direction without having to like a two-wheeled robot has to like turn and then go this way and then turn and then go that way. But this robot, because it's spinning the whole time, all it really has to do is like at that given point in its rotation, make the wheel go faster a little bit. So it can hypothetically change directions, just like if it had Omni wheels, like you see Shatter doing, from any orientation. But it will never be able to move nearly as fast in any given direction as a robot that uses the traditional drive system. Now, let's talk about something completely different. Something that is just a research project robot and in no way intended to see combat, but that has a lot of the same kind of complexity and sensing problems that you would run into if you tried doing some complicated stuff in a BattleBot. So this is a robot that is a cube. And this robot operates basically by spinning a bunch of gyroscopic wheels, kind of like you see with the spinning weapons on BattleBots. And basically, every time one of these wheels accelerates or decelerates, it can torque the whole cube, which allows it to do crazy stuff like balancing on one end or like forcing itself to roll and all this other crazy stuff. Some people have suggested to me that I try to implement a system that's like this in Division with the weapon, such that it can basically react to disturbances and stay upright all the time. Now, yes, obviously this is physically possible. You can see it doing it right here. It's clearly a thing that can be done by PhD researchers in a robotics lab. It is not something that can be done by me with my mechanical engineering degree and almost no real robot controls experience outside of that couple classes that I took, of which I use none of in my daily work as a mechanical engineer or for building combat robots. But I would like to at least point out that this is a thing that exists and it's pretty cool. So yeah, but I mean, look at this thing. It's super fragile. There's a gigantic circuit board. There's like a bajillion little wires and electronics. Like literally every single inch of this is packed to the gills with all of the sensing and electronics needed to make this thing work. And none of that is like battle hardened. None of that is meant to withstand hundreds or thousands of G-forces that can be experienced in a combat robot impact. So I think just the added complexity in general is one of the main deterrents from using any kind of system like this in a BattleBot, even though it is pretty cool and there would be some obvious advantages to like automatically stabilizing whether your robot is upright or not, or even being able to like cancel out gyroscopic forces during turning and whatnot. Okay. Now let's look at some examples of how this might actually be able to be implemented in a way that's not entirely awful in a BattleBot. So what I've got behind me is a really simple system that's part of a testing rig that I'm planning on building, which I'll show off in a future video. Right now it's kind of a super secret project that I'm working on in the background until I get it to a point where it's actually ready to be shown off to the world, since I still might never finish it. So right now I've got my webcam here, hopefully you can see on the top left. So this is basically the Division version 3 chassis that I ran in March with the gas in it completely fine. I've got a different motors, one motor using Division version 1, and I've got my laptop back here, and that is hooked up to this Autonomy sensor, which basically just senses when magnet goes high. I've got 4 magnets embedded in this thing, and all that this is doing right now is telling me how fast the thing spins. So I've got to turn on my transmitter here. And you can also see I've got the same receiver that I use in Division version 2, so the electronics that I use in Division version 2, 3S battery, this is really big because I just want to run out for the 6 demo. Turn on the LED 32 controller, this is the EC power you can see right now. So this isn't controlling, this right now here isn't controlling anything. All it's doing is sensing how fast this spins, and then recording that back from the laptop. So I'm going to switch both again. Ignore the CMD thing because that's not doing anything right now. So you can see SPDW changes as I bring up the throttle, and it does more or less what you'd expect. The further I push up the throttle, the faster it spins. All right, I'm going to show you next how I can implement a little bit of autonomy into a combat robot. But first, let's talk about today's sponsor, PCBWay. PCBWay offers CNC machining service that I've used before in several combat robots, as well as a PCB fabrication service that they're very well known for, which I used for the power distribution boards in my 3-pound combat robot Division, which previously fought with that very chassis over here. Now, You might have heard of Arduino before, but might not know what it is. This is an example of an Arduino Nano, which is the same exact board that I have right by Division's chassis right now. And this board is basically just a tiny little crappy computer that does math really fast, but not much else. And it allows you to interface with different sensors and speed controllers and servos and motors and all sorts of stuff. And it can be programmed in a programming language called C, which is basically a modified version of C, really, called Arduino code. But it essentially is a little computer that does math, but not much else. Now, normally it looks like that, but I have added a custom PCB made by PCBWay that looks like this. This is basically a breakout board that allows me to easily connect the Arduino Nano to speed controllers like I have and sensors like I have behind me here. So you can see that normally we have these 3-pin servo connectors, and these servo connectors don't easily interface with just a bare Arduino board because you need to connect each one to a ground pin and a signal pin, not just to one pin for each of these signals. So by creating this board, basically splits the ground, signal, and 5-volt, 3-volt out into convenient 3-pin arrangements so that I could more easily connect everything up. I'm going to be using this or similar board in future projects, and it's what I'm able to use today to make this easy to demonstrate for all of you guys. Make sure to check out PCBWay at PCBWay.com and use the referral link in the description so you get $5 off your next order. Okay, ordinarily I record my voice with RTX voice enabled to disable background noise. I've turned that off now so that you can hear the weapon spinning and stuff, and I've turned up the gain a lot, so hopefully you can still hear me talking when I'm not facing the microphone. So what you should be looking at here is we've got the Arduino. Now previously I only had this cable hooked up, and now I have this one hooked up as well. This cable goes to the speed sensor, which is right here. And then this black and white cable just goes to the speed controller itself that tells the motor to spin. So instead of before where I had the radio telling the motor to spin, now I only have the battery and the Arduino connected and the speed sensor. So what should happen is I type in a speed and then it goes to close to that speed using closed loop feedback. Let's try 1000 RPM. So you can see now, hopefully you can now see that it is spinning close to 1000 RPM with SPDW reporting the weapon speed. CMD is reporting the microsecond pulse width that is being sent, which is the same kind of signal that a receiver would typically be sending. Let's try pushing it down to 300 RPM. Alright, now it's a bit quieter, so hopefully you can hear me a little bit better. So you can see here, this is an example of closed loop feedback where I've got the speed sensor determining exactly how fast that the thing is spinning by sensing the magnets as they pass by, and communicating that back to the Arduino, which then adjusts the command signal sent to the speed controller in order to maintain a fixed speed that I choose. Let's try going even faster. This is going to get kind of loud. 4000. Now 2000. And now 0. So that is an example of closed loop control. You can see that I was able to basically tell it exactly what speed to go at, and it would try to go at that speed. That last test may have seemed a little bit pointless, given that really it was fundamentally the same as pushing a stick up and down on the radio to get the speed to change. I was typing a number into my laptop and sending it instead. But the idea is that because it was being driven by the code running on the Arduino, I could make it do all sorts of other things as well, or have it respond to sensor feedback from some other system, etc., etc. So really the possibilities are endless. It's just a matter of what can you actually implement yourself, and can you get it to be robust enough to work in combat, which is usually a pretty tall order. So personally, I'm not planning on doing an autonomous robot anytime soon, but there are people like Pearl Grey with their robot data collector, who are trying to push to get some sorts of semi-autonomous control, like making it so that the robot drives in a perfectly straight line when it needs to go straight and turns nicely with weapon gyro managed automatically, so that they don't have to focus on doing everything like I do when I'm driving Division. So there definitely will most likely be some more autonomy in robots in the future, but for the moment, it's just so much effort for so little payoff that for, 99% of use cases, there's really not much point to it. So I still feel that Battlebots are robots regardless of how much autonomy they exhibit, but there's definitely room for improvement in that regard in the future. That's all I've got for you today. If you enjoyed this video, make sure to click like. If you want to see more videos like this, make sure to subscribe and click the bell icon to get notified. I will definitely be releasing a video at some point when I finally finish that secret project to show a lot more about it. So make sure that you've clicked the notification bell for that. And as always, thanks for watching.